When examining the relationship between two quantitative variables, we've already seen how much information can be gleaned from a simple scatter plot. In this video, we're going to learn about ways of describing this relationship more precisely, both verbally and numerically. So we'll start off by talking a little bit about correlation. So let's take a look at some real data. This data comes to us from Old Faithful. For those of you that don't know what Old Faithful is, it is this beautiful geyser that is in Yellowstone National Park. Draws a lot of spectators. Unfortunately, does not always erupt at predictable intervals. So of course, we have to think about ways of modeling when it might erupt next. What we're trying to do here is look at the relationship between how long a current eruption of Old Faithful lasts and how long we have to wait until the next eruption. So what we see first is a scatter plot here, plotting these two variables against each other. By the way, one of my pet peeves is hearing someone mistakenly call a scatter plot an XY plot. The XY plot is just the name of the function that we would use in R to produce a scatter plot, and the plot itself for showing two quantitative variables is called a scatter plot. You're really never going to find mentions of an XY plot when you're reading a research article. In any case, back to the data. So what we see here, I hope you guys will agree, is a very vague positive association between these two variables. And we can see that because this cloud of points is positively sloped. Okay, so we can certainly see that visually, but of course we want to be able to think about ways of describing this picture in case we're trying to communicate our observations to someone who doesn't have the scatter plot right in front of them. So several things you can note about a scatter plot, and these have to do with what we call direction, form, and strength. So these are keywords you want to be able to get in your head when you're thinking about describing the relationship between two quantitative variables. With direction, we are talking about either positive or negative. If you're trying to draw this cloud, does that cloud seem to go up from left to right, or does it seem to go down from left to right? In our case, the answer is that it is positively sloped. When we're talking about the form of a scatter plot here, we're really thinking as long as we have seen no evidence of bends or curves, as long as we see no evidence of nonlinearity, we're going to go ahead and call that linear. In this case, it's a pretty straightforward case of linear because we do not see any evidence of bends or curves in this scatter plot. Finally, we're going to talk about strength. If you tell me the value of one variable, how surely can I tell you what the other variable is likely to be? Put another way, we can talk about strength as how tightly clustered to, say, a line or some other kind of pattern these points happen to be. So correlation is really directly relating to this thing called strength, right? So we want to be able to quantify the strength of the relationship between two quantitative variables. And of course, correlation doesn't really apply to all sorts of relationships. It's really only going to pertain to relationships that are linear. So if we look at this plot and we see a linear relationship, then we can proceed to use correlation to describe just how strong that relationship is. So we can actually write out a formula for correlation, and here it is. So there are some terms that we haven't quite discussed here, so I'll go through these in a little bit of detail. N here is the number of observations that you see. Put another way, N is the number of points that you would find in a scatter plot. Another thing that we perhaps have talked about briefly, but not in too much detail, is this X bar and Y bar. These are the means, the sample means of those two variables. Now what we also have to know is some of these terms in the denominator, S with a subscript of X being the sample standard deviation of X, and S subscript of Y being the sample standard deviation of Y. So standard deviation we've seen when we talked about the normal distribution, and what it really is the square root of the average squared distance from each point to its mean. So to calculate correlation, say in R, it actually becomes a lot easier because you can imagine there's a function built into R, in fact it is called COR, C-O-R, that will calculate correlation directly for us. It turns out the correlation can be a value that goes anywhere from -1 to +1. And the larger R is in magnitude, meaning the closer it is to -1 or +1, the stronger the relationship between the two variables at hand. And the closer that R is to 0, the weaker the correlation between the two variables. So these are just some rules of thumb that I would use when describing the strength of the relationship between two variables on basis of their correlation. Let's look at an example here. So generally on an exam, I wouldn't make you calculate correlation from scratch for the reason that the summation there is going to include a lot of terms, a lot of different opportunities to make a slight error, causing you to get to the wrong answer. But I could easily give you a question like this. Suppose you have fast food data relating to body fat in grams and sodium in milligrams, and our question here would be, are the two variables related? So just applying the formula, here we are. Some of you might note that fat content and sodium content are actually measured in different units, and you know what? That's actually not a problem. Correlation is a unitless quantity, and it doesn't matter whether you had maybe translated the sodium content into grams, you would end up with the same exact value of R. In fact, I would challenge you guys to try that just to show that you arrive at the same answer, and that answer is going to be 0.199. So looking at that value, we then might answer the second question. Given that this is a positive R, we would say that yes, the two variables are positively associated. And the second part, in terms of the strength, because 0.199 is quite low, I would say that this is pretty weak. Let's look at a different example. So here we have a lot of data now, in contrast to the previous question. We have 1,302 UCLA students filling out a survey asking about their height, the fastest speed they have ever driven, and their gender. So what we have on the left here is a scatter plot where we're just looking at the fastest speed driven against height. And so looking at this plot, the question is, can you describe the relationship between height and fastest speed? So to look at this plot, the first thing we want to note is there are some interesting things happening there. I'm not quite sure what those values correspond to, but presumably they are really, really, really low values for height. Do we particularly believe these values? Probably not, for the reason that they seem not to fall within the pattern that we would see within the cloud of points over here. So perhaps we would think about just ignoring those four values in the absence of better information. Similarly, we have a lot of values down here. Even at the college level, there are instances of students who have not gotten their driver's license, who perhaps don't own a car and have never driven a day in their life. So my guess is that these folks down here correspond to that cohort of students. But in any case, we should focus in on the relationship that we see in this plot. And what I see here is certainly a positive, very rough positive sloping cloud of points. So I'm going to write positive. Now, would I say that this is linear? Probably, because again, I don't see any bends, any curves in this plot. And finally, I would say that this is a very weak relationship because, you know, this slope doesn't seem to be very, very large. For the most part, it looks like it's just got very little relationship between height and fastest speed. Now, part B asks us to think about why these variables might be positively associated. Well, the second plot is interesting because it has added another dimension to the plot, and that corresponds to gender. We're now seeing that there are two distinct clusters of people. We have females who are shorter because the X's in this plot happen to be shifted lower than the solid circles on the right. Perhaps men just drive faster than women in our data set. So this is a classic case of where gender is a confounding variable. Yes, gender can explain the differences in fastest speed driven, and similarly, gender explains the differences in height. Let's now go back to the Old Faithful data. So having determined the relationship between waiting time and duration to be linear, not only can we talk about correlation to quantify the strength of the relationship between the two variables, we can also more precisely define that relationship using an equation. And this is where simple linear regression comes in. Simple linear regression is a tool for us to be able to specifically write out an equation that relates a y variable, which we call the response, to an x variable, the predictor. And what we do is we come up with an equation that looks like this. So we want to get an intercept, we want to get a slope, and anytime we pop in some value for x, in this case duration, we can use this model, this equation, to come up with an estimate of waiting time. So this hat on top of y, that is to remind us that indeed from this equation all we get is an estimate. It's not going to give us the exact value of waiting time, it's just going to give us our best guess on basis of the data that we have. So before I talk about how we actually fit this model either by hand or by using R, I want to talk about how we actually arrive at this equation mathematically. But why should that line be the line that we use to describe the relationship? For example, why don't we use this line, or that line, or maybe this line? After all of these lines go through this cloud of points pretty well. So what we're actually doing when we fit a linear regression model is we are paying attention to this thing called the least squares criterion. So with the least squares criterion, what we're doing is we're choosing the line, meaning we're choosing values of the slope and the intercept such that we minimize a quantity. So what we're doing is taking each value in my data set. So in this case, if I have, say, 50 values in my data set, then I'm actually summing over 50 terms in the summation. Every term is going to correspond to the y value of a point minus the predicted value. So what we're looking at in the summation is really a bunch of square distances from each point to any line that we're drawing. Okay, so these are just some such vertical distances that I'm drawing for some of these points. But you can imagine squaring all of these distances and then adding them up. What we're doing when we're fitting this simple linear regression model is choosing values of b0 and b1 that minimizes this sum of square deviation. The line that we choose has to be the line for which these vertical square distances summed up together is kept to a minimum. You can certainly use some calculus to figure this out pretty precisely, right? So what we're basically doing is trying to calculate B0 and B1 subject to minimizing this quantity. So if you use some calculus, what you're going to end up finding is that we have these two equations that we can use to calculate the slope and the intercept. And these ingredients that go into these calculations, we already know. So for example, with the slope, we know that one of the quantities here is the correlation that we already know how to calculate, as well as a ratio of standard deviations. Now make sure you see that it is the standard deviation of y that goes in the numerator and the standard deviation of x that goes in the denominator. Simple way of remembering this is just rise over run. And then after calculating the slope, we can plug that back into this first equation to figure out what the intercept would be. And the only other components in this calculation are going to be the sample means of your x and your y variables. So if you use a little bit of algebra, you can actually show, using these two equations over here, that the line that we choose will ultimately go through mean of the x as the x coordinate and the mean of the y's as the y coordinate. So of course, if you have your calculator, you can do this calculation by hand, but if you have R, this is actually a lot simpler. You guys remember how we do a scatter plot to begin with? We simply do XY plot of waiting tilde eruptions, data equals faithful. All we have to do is replace XY plot with LM for linear model. And then what I can do is run the summary on this model that I've created, and what I'll get is a lot of information. The only thing we need to see now is what's in this column. So what this is telling us is that our value of B0, the intercept, is 33.47, and it tells us that our value for the slope is 10.73. Just to sum things up, okay, so all I've done is plugged in the values from my linear regression output to find the intercept and the slope, and most important thing here is putting the hat on my y variable, weighting, just to indicate that I'm not saying that I can use this right-hand side to calculate the precise waiting time. It is only going to generate an estimate. So always keep your hats on when you're giving estimates. So how do we actually interpret this 33.474? It is the value of y when x is equal to 0. In this case, we don't have any data near 0, meaning we don't have any eruptions that lasted 0 minutes. So really this prediction is somewhat meaningless. But theoretically, it would be telling us that an eruption lasting only 0 minutes is expected to be followed by a waiting time of 33.5 minutes until the next eruption. The slope, the 10.730, this is more interesting. It's suggesting that a 1 minute increase in duration is associated with an average increase of 10.73 minutes in the waiting time until the next eruption. To close off, I want us to come back to this scatter plot once again. And I hope you're realizing that a linear regression model may not really be appropriate here. Why? Because not only do we see this positive association, but we also see what seems to be two distinct clusters down here, corresponding to eruptions of short duration, and a cluster up here, corresponding to eruptions of longer duration. However, this is an illustrative exercise for examining how linear regression works for the first time.